Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing great today. I am Azmat Ali and I welcome you all in class of elementary number theory by David M. Burton. In today's lecture, we will discuss some problems related to mathematical inductions. So let us start from problem 1.1. Establish the formulas below by mathematical induction. We discuss the A part of problem 1, that is actually the sum of first n natural number is equal to n into n plus 1 by 2 for all n greater than or equal to 1. So this is our first problem in which we have to show the first n natural number having the sum equal to n into n plus 1 by 2. The mathematical induction is a method to prove formulas or mathematical statements that consist on the following three steps. First is the base step. First of all, let the given statement is denoted by P of n. That is P of n such that 1 plus 2 plus 3 up to so on n is equal to n into n plus 1 over 2. Now we perform the base step. The base step says we check the statement for n is equal to 1. So put n is equal to 1 here. When n is equal to 1, from the left side we get 1. And when we put n is equal to 2, we have 1 into 1 plus 1 over 2, which is equal to 2 by 2 and which is equal to 1. This shows that left hand side is equal to right hand side. That means the statement is true for n is equal to 1. This implies statement is true for n is equal to 1. That is, the base step is true. Next we move to the inductive hypothesis. That is actually the second step. Suppose that the statement is true for n is equal to k, where k is any integer. Inductive hypothesis. Suppose that statement is true for n is equal to k, where k is a positive integer. K is greater than or equal to 1. This implies P of k such that 1 plus 2 plus 3 up to so on k, that is the sum of these k integers, is equal to k into k plus 1 over 2. This step we can obtain simply by just putting n is equal to k here on both sides. So suppose this is our question number 1. Next we show that the statement is also true for n is equal to k plus 1. That is the inductive step. Next we move toward the inductive step. Here we show that pk plus 1, that is pk plus 1 means the statement for k plus 1 is true whenever statement is true for n is equal to k, whenever pk is true. So here what would be the statement for n is equal to k plus 1? Statement for n is equal to k plus 1 is here. Statement for n is equal to k plus 1 is here 1 plus 2 plus 3 up to so on k plus k plus 1. These are the actually sum of first k plus 1 natural number, and this should be equal to k plus 1 into k plus 2 over 2. The right side you can obtain by simply putting n is equal to k plus 1 in the right hand side of the given question here. So I will use question number 1 and take the right hand side of this expression to prove the truthness of this statement. So we choose the left hand side 1 plus 2 plus 3 plus k plus 1. Next, by using question number 1, in this equation the sum of first k natural number is given by this k into k plus 1 by 2. So we substitute this sum, this whole sum is equal to this. So this is equal to k into k plus 1 over 2 plus k plus 1. Just taking k plus 1 common, we have k plus 1 k over 2 plus 1. By taking LCM, we have k plus 1 into k plus 2 over 2, which is equal to right hand side of the pk plus 1. That is need to show. This shows that pk plus 1 is true whenever pk is true. Hence, by mathematical induction, as all three steps are completed, hence by mathematical induction given statement is true for all positive integers. Similarly, we try another question. So let us discuss its D part. In D part, we need to show that the sum of squares of first n odd natural numbers is given by n into 2n minus 1, 2n plus 1 by 3 for all n greater than or equal to 1 here. Okay, let us discuss its D part. Let you can write, let Pn be the given statement, so we call this is our given statement, that is Pn. First step is base step. So let us check the given statement for n is equal to 1. We have P of 1 is equal to, the left side is given by 1 square, and for the right side we put n is equal to 1 here. We have 1 into 2 into 1 minus 1, 2 into 1 plus 1 over 3. This is equal to 2 minus 1, 1, 2 plus 1, 3, 3 by 3, which is equal to 1. While here 1 square is also 1, so the given statement is true for n is equal to 1. Next we move towards the inductive hypothesis. That is the second step of mathematical induction. Suppose the statement is true for n is equal to k here. We have P of k 1 square plus 3 square plus 5 square up to so on 2k minus 1 whole square is equal to k into 2k minus 1, 2k plus 1 over 3. Suppose this is my equation number 1. Next we show that the statement is true for n is equal to k plus 1. What would be the statement for n is equal to k plus 1? This is simply obtained by just putting n is equal to k plus 1 on both sides of the given question. So we have the statement for n is equal to k plus 1 is given by 1 square 3 square plus 5 square up to so on. This is the second last term, which is given by n is equal to k, and the last term for n is equal to k plus 1 is this 2k plus 1 whole square. You can obtain this term just by putting n is equal to k plus 1 in last term. So when you put n is equal to k plus 1 here, we have this is 2k plus 1 whole square is equal to, what is the right hand side when we put n is equal to k plus 1 here? We have right hand side is for n is equal to k plus 1, k plus 1 2k plus 1 into 2k plus 3 over 3. By putting n is equal to k plus 1 here, we have 2k plus 1. When we put n is equal to k plus 1, we have 2k plus 3 over 3, where k is positive integer greater than or equal to 1. So now we take left hand side of this expression and we use the truthness of 1, and we show that the right hand side of this expression. So let us take left hand side 1 square plus 3 square plus 5 square we take separate the first k term as, because I will substitute here the sum is equal to k into 2k minus 1 into 2k plus 1 over 3 from 1 plus, what is the last term here? This is 2k plus 1 square. By using 1, this sum is equal to k into 2k minus 1 over 3 uh, k into 2k minus 1 into 2k plus 1 over 3 plus the last the second term is 2k plus 1 square plus 2k plus 1 whole square. Taking 2k plus 1 common from both terms, we have 2k plus 1 k into 2k minus 1 over 3 plus 2k plus 1. By taking LCM here, we have, and multiply k inside the bracket, we have 2k square minus k plus 6k plus 3 over 3 minus k plus 6k, this becomes 5k, and after making the factor, this is 2k plus 1, this is equal to 2k square plus 5k plus 3 over 3. Now we make the factor of this quadratic expression. What are the factor of this quadratic expression? These are simply 2k square plus 2k plus 3k plus 3 over 3. 2k plus 1 by taking common 2k, this becomes k plus 1 plus common 3 from here, we have k plus 1 over 3, and this gives us 2k plus 1 into k plus 1 into 2k plus 3 over 3, which is the right hand side of pk plus 1. Yes, so we will write hence the statement is true for n is equal to k plus 1 whenever statement is true for n is equal to k. Hence, by the mathematical induction, given statement is true for all positive integers. I hope the remaining parts you can solve easily. Also, you can solve question number 2. So we will discuss in the next lecture from question number 3. So if you find this lecture is helpful for you, kindly like and share. So take care. See you in the next lecture. Allah Hafiz.